the motivation of this little mini series of sessions is going to be to sort of bring up to speed the two rotation students in my lab, and to give Eric, who hasn't been at any of our Eman workshops because we didn't hold any during the pandemic, and other beginners in my lab, an introduction to some of the stuff required for single particle analysis and subtomogram averaging in Eman. I'll also cover some of the dynamic stuff at the end, which is brand new. And I and Muyon have talked about sort of versions of it in the past, but never really gone through it in sort of a tutorial form before. So that's more or less the plan for this little sequence. So the goal is that today I'll give a little introduction, more or less the form of a lecture. I don't expect that anyone will have already done anything before today. Then during the week till next Monday, I'd like everyone who's participating to go through the single particle analysis tutorial. That's very robust and straightforward and easy to go through. If you've gone through it before and you're comfortable with all that stuff, that's fine. But the goal of these sessions is not for me to handhold you step by step through the tutorials, which are already pretty thorough, but to give you an opportunity to ask questions and to look over the results in sort of a group and make sure that everyone sort of understands what you should see and what you shouldn't see and that sort of thing. So in the first week, we'll target the single particle analysis tutorial. In the second week, we'll target the subtomogram averaging tutorial. And then in the third week, we'll target the dynamics. If we wind up doing a lot more discussion and getting in depth, we may stretch that out for another week or two. Beyond that, we'll just have to sort of see how things go. But today we'll just start out with this little lecture. Before I start with that, let me go to the EMAN2 webpage. Right, if you go to eman2.org, you'll get this nice web page, and under written tutorials, you will find the single particle analysis tutorial. So this single particle analysis tutorial right here, this is what I'm hoping that everyone will go through before next week. If you haven't used any EMAN2 before at all, then I would recommend also taking a look at this quick introduction to the EMAN2 GUI tutorial. And as part of the single particle analysis tutorial, you might want to take a look at the particle picking tutorial or the tutorial for the neural network particle picker. The single particle analysis tutorial makes use of pre-picked particle locations, so it sort of skips that step. So these tutorials may also be useful, and you're welcome to ask questions about them when we talk next week. Of course, to do that, you'll have to have Eman2 installed. The installation instructions are on the previous, the main page. Install Eman2. Installing from source is actually not much more difficult than installing the binary. And I strongly suggest, particularly if you want to do some of the dynamic stuff later, that you be using a current snapshot of Eman2 rather than the 2.91 release, which is now like a year and a half old. So I would kind of suggest just going ahead and installing from source. If you really don't feel competent to do that, you can do a binary installation, but if you do that, use one of the snapshot versions, not the 2.91 release version.
For the rotation students, Eric and I can help. I think we're both pretty good at it, the installation.
Yeah, sure. So if you have any difficulties with any of this, feel free to email me, or if there's someone in your lab or whatever, you can talk to them too. But anyway, feel free to seek help as necessary with any of that stuff. Once you have Eman installed, probably you can get through the tutorial. It's been revised over many years, and it's pretty well put together at this point. So the first week we'll be doing this single particle analysis tutorial. Then the second week we'll be doing the tomography workflow tutorial. Even if you've done that before, I would suggest maybe going through that again, because it was recently updated. Recently meaning just like a month or two ago, maybe even only a month ago. I actually went through it. There used to be a large tutorial and a small tutorial, and it was a bit out of date in various places. So it's now been merged into a single tutorial with a small and a large option internally. And it includes all of the modern versions of the software that work much better than the first version that we taught people how to use. So anyway, I would suggest going through this version, and I ideally you'd want to use the large version of the tutorial rather than the small version. You'll have a week to do it, so it shouldn't be any trouble doing that. You may not be able to do the large one easily on a laptop, but it depends on the laptop. Then there isn't a tutorial yet for the dynamics. Well, there is a tutorial, an old tutorial Muon put together for the dynamics, but it's based on going through Jupyter Labs and doing a bunch of manual stuff there. We now have an integrated GUI for the dynamic stuff, which is actually working pretty well. It's still a work in progress, but anyway, I'll see what I can put together before that time. So, right. Any questions about any of that?
Well, I had a thought. Just maybe you could use some of us too if we're finding things that might be worded more easily, to make edits too. Eric and I have both suggested it to both me and Eric at some points. So that might also be, we could do that in parallel a little bit.
Any suggestions for improving the tutorial from anyone in this group are absolutely welcome. The single particle tutorial is provided as a PDF. It's not an editable online document, so you'd have to make a list of notes for that. The tomography tutorial is actually part of the wiki. So anyone who has wiki edit permission can actually make modifications to that. Whether it's a good idea to do a lot of those modifications during the week when people are going through it or not, maybe not. I would say only make either sort of trivial correction kinds of changes or changes which are necessary to improve the clarity of what I'm asking you to do, like additions rather than removing or reorganizing or anything like that during that time. And anyone who doesn't have and would like editing permission for the wiki just has to ask. It used to be that it was actually open and anyone could sign up and make changes just like a wiki is sort of supposed to be, but then of course we had spammers come in and spam bomb the entire wiki. So now if you want an account on the wiki, you have to actually ask me and I'll set up an account for you. But I have no problems doing that for anyone who's interested in helping with documentation. Okay. So
I've just one other comment. It would be great. So like what I found with the tutorials are they're very clear and very good, but it's not always easy to get the sought after resolutions. So what I was just maybe as we go through it, you can suggest certain standards for each, certain checkpoints. Like at this point, really needs to be of such and such a quality, and this point, so we can get.
I think the single particle tutorial at least does that.
Okay. All right.
It has a sequence of resolutions that you're trying to achieve, and it sort of shows you what it should look like in most cases. Anyway, one of the big things that we're going to be doing here is then, people go through the tutorial to the best of their ability, and then we'll look together sort of at the
Okay,
results.
that's great.
And if your results don't look like what the expected results are, then the idea would be to try and figure out as a group why.
Okay, great.
Yeah. So that's the whole point of doing this kind of session, is to sort of help people get that aspect of things which you can't easily get from just reading the tutorial itself. Okay, so a little introductory talk on single particle analysis. Eman has been around for a very long time now. I guess released it in 1999. And I'll point out that even though Phil has done a bunch of things in between, Phil was part of Eman from the very beginning. So we started developing it back in 1997, 1998 or whatever, and then the first version was released in 1999. It did a number of things sort of first, which was the first to do sort of pure Fourier reconstruction for single particle analysis, with the caveat that people who were doing virology were using Fourier Bezel reconstruction before that. I'm not saying that no one ever had the idea of doing anything in Fourier space. Fourier space was used very heavily, just that the idea of instead of doing back projection, doing direct Fourier reconstruction, which I'll explain, is kind of novel. Surprisingly, somewhat, Eman was also the first to really do full CTF correction and make it publicly available. Spider also started doing it, over the next, could do it, the people who were developing Spider could do CTF correction, but they hadn't really made it publicly available at that time. And they didn't really get it integrated until a few years later. Anyway, so Eman had a bunch of things that was first 20 some odd years ago. So then this is sort of a timeline where things fit in. There was a project briefly. You may notice that Eman is distributed with something called Sparks and something else called Spire. Sparks was actually originally a collaboration between Paul Adams, Paul Penchek, and my group. And the goal was to produce a combination of EMAN2 and Phoenix, Phoenix being an X-ray crystallography software package. And ultimately, that goal turned out to be kind of premature. We did some stuff, but it wasn't really interesting at the time because there was such a big resolution disparity between the two fields. Now those things have actually begun to really emerge, 15, 20 years later. Anyway, eventually that grant ran out, and Sparks became Paul Penchek's project. So he started developing his own single particle code and gave it the name Sparks. But it was still sort of jointly developed, shared a lot of code base with Eman2. So they're still jointly distributed to this day, although Paul Penchek is now retired. A lot of the stuff with Paul Penchek turned into Spire. That's what you see down here via collaboration with Stefan in Germany. Which was the idea to wrap some GUI stuff around Sparks. So now Spire is also jointly distributed with Eman2, and they haven't been real active recently, but that still does exist. Anyway, that was probably more history than we really need. You can just sort of see where various things happened over time. Obviously, recently, we've seen Relion and CryoSpark have sort of taken over the market for single particle analysis anyway. Relion is also getting into subtomogram averaging, having sort of absorbed some of the developments by other groups which tried to tack that capability onto Relion. But there's still some competition in the subtomogram averaging field. So single particle analysis, right? Basic idea is you take a bunch of images of individual particles like this, and then put them together to produce a big, nice high resolution single particle reconstruction. So this was actually the reconstruction which first led to Relion's popularity, because he managed to solve this high resolution ribosome structure using data collected in like a day, and then did the reconstruction over just a few days. So like in a week, he had this high resolution ribosome structure, and the best ribosome structure that Joachim Frank had managed to produce in 20 years before that was at worse resolution than this. So this was what really gained Relion its first attention in the field. Now, key point to understand, particularly for those of you who are new to single particle analysis, is that when you collect images on a transmission electron microscope, what you're getting are projections. You're getting sums through the object in question. It's also modified by various factors in the microscope, which we're going to be talking about, but you're not seeing some sort of a surface view or a slice or something like that. So, if you're doing optical microscopy, like confocal or something like that, you're looking at slices. There are various microscopies where you may be looking at reflections off the surface. No, tomography is basically a pure projection through the object. So when you look at an object in one direction, you're getting all of the information through the depth of the object, except for the information along the path where the data is being summed. So if you look along, the beam is going this way, you'll see an image like that. It's not giving you any information about where the density is along this axis, along the projection axis, but it is giving you information about what's happening at every point in the axis. It's just confused along that direction. But then if you combine that information with information from another direction, then that gives you information about what's going on in this direction. It just doesn't give you any information about what's going on in this direction. By combining that information from all the different orientations, you can do a 3D reconstruction. So this is just a quick overview of the single particle reconstruction process, the whole thing, right? You prepare grids, you record images, you do your movie alignment, extract the particles, determine orientations, do a 3D reconstruction, and then you interpret your map. So whole pipeline. Today, we're just going to be limiting ourselves to these steps of the process. I'm also not going to talk about particle extraction, which is particle picking, locating the particles in the frames today. That's what those other two tutorials are about, if you want to take a look at those. But that process is straightforward in the sense that, you know, you have an image and there are particles all around. You just have to figure out where the particles are. So the next step in the process is to determine the orientations of the particles. So to do that, we have to have a set of references. So we have an individual 2D particle in some unknown orientation. We need to figure out what that orientation is if we want to be able to do anything with it. So the way that is typically handled in the field is by generating a set of exhaustive projections in all possible orientations. Now what we're looking at over here, is a set of projections of the ribosome covering all possible orientations with the 7.5 degree angular step. So each frame in this movie is spaced by 7.5 degrees from the previous frame. And you can see there's a large number of projections. Now, think about for a typical single particle reconstruction, you actually need 1 or 2 degree accuracy. So you're actually generating a humongous number, maybe several thousand in many cases, projections. And then the goal is, ostensibly, you need to compare each individual collected particle with all of the generated projections and figure out which one it looks the most like. Now, if we just do that in a very naive fashion, so say we had 30,000 particles, which is quite small by modern standards. I mean, most cases you have 10 times that many or more particles. And 3,000 projections, which would correspond to a 2.6 degree angular step in that little movie I just showed you. And then you needed to sort of exhaustively compare. So not only do you need to figure out the correct 3D orientation, but the particle in 2D in the plane has to be centered and it has to be rotated in the plane in the correct orientation. So let's say we're going to look at 180 possible rotations in the plane, and we'll assume when we pick the particles, we've got them kind of well centered already. So when we're picking our particles, we're only going to look in a box 10 plus or minus 5 pixels from the center. So if we work all this out, it's going to take a total of 2.1 times 10 to the 18th floating point operations to do this exhaustive search to solve this problem. If you work out how much that would take about 240 days to do the necessary math on one typical workstation. And this is a pretty small project. So clearly, the way we're accomplishing this orientation determination, that sort of thing, is not by exhaustively searching every possible orientation, every possible particle. We're being a lot smarter about it than that. Yeah, and just a note. So on EMAN2, the time for this is about 3 hours. So that's a big factor. 240 days down to 3 hours. So obviously there's a lot of this stuff that can be skipped or optimized. Once you got the orientations of the particles, then you do 3D reconstruction. There are a bunch of different algorithms which have been used historically to do 3D reconstruction. If you do tomography, you'll still find back projection, filtered back projection, and CERT in use commonly. So if you use IMOD to do your reconstructions, filtered back projection is still sort of the default operation, and you can do CERT if you're willing to wait a while for the results, because it's an iterative process which takes some time. The method that's used now pretty much universally for single particle reconstruction is direct Fourier inversion. I'm going to assume that everyone here knows a little bit about Fourier transforms, because that's another hour-long lecture, which I don't want to give today. If you don't know anything about Fourier transforms at all, I would suggest watching some YouTube videos like watch some of Grant Jensen's videos maybe, or just look up videos on Fourier transforms and try and learn a little bit about them. The goal isn't to become a mathematician or understand them at a mathematical level necessarily, but to at least to sort of have a general idea of what Fourier transforms are and represent. But from a very simplistic perspective, a Fourier transform takes an image and it produces another image, and you can go from this image back to the original image without losing anything. So this is an alternative representation of the image. In the Fourier space, the middle represents very coarse, very low resolution features, and the edge represents very high resolution features. And then the direction in the Fourier transform is the same as the direction in the original image. So features, the high resolution features in this direction are sort of represented here in Fourier space, and low resolution features in this direction would be represented by information down in here. That's my quick introduction to Fourier transforms. So anyway, once you know the orientations of each of the particles, doing a 3D reconstruction is actually really easy if you go to Fourier space. So you take each particle in its known orientation, you take the Fourier transform, and then you insert it into a three-dimensional Fourier volume. And the orientation that you insert it in is the orientation that you determined the particle was in. And by inserting all those slices, you can then invert the 3D Fourier transform and get out the final structure. Now, obviously, I've only put 4 particles in here. If you have 100,000 particles, then it's going to completely fill in this space. Hopefully, it's going to completely fill in the space. There are issues with preferred orientation and stuff like that, where you may have some gaps still in Fourier space, which causes some artifacts in the image. But the idea is that you would have uniformly distributed particles, and with enough of them, that it would sort of fill in Fourier space. Now, we have a little problem you may have noticed, which is to determine the particle orientations, I said we needed to have a 3D reference, which we would then make projections of. But if we already have a 3D reference, then why do we need to do the reconstruction in the first place? Because we already know the structure. So that's a little bit of a catch-22. So all current cryo-EM single particle reconstruction solutions are iterative solutions. What that means is you start out with some sort of a vague guess of what the 3D structure is. And then through iterating, you start out with a vague guess, you determine the orientations, you get a 3D reconstruction. Anyway, so there's an iterative process involved. And different software packages of the field use different strategies, but they're all iterative strategies. So if you look at sort of the original single particle reconstruction, generic single particle reconstruction package in the field, which was SPIDER, developed in Joachim Frank, who won the Nobel Prize for his ribosome cryo-EM work. So SPIDER was developed in the late 70s. It's written in Fortran 77. It was finally first published in 1981. Anyway, this was the original package, and the strategy it uses is extremely straightforward. It's basically what I just explained. You start out with some sort of initial model, you make projections, determine the orientations using the projections of the boxed out particles. That gives you a 3D reconstruction. From the 3D reconstruction, you make new projections, redetermine the orientations, make a new reconstruction, and you just keep doing that process over and over again, maybe 10, 20, 30 times. And eventually you get out a 3D structure, which is hopefully the correct answer. The nice thing about iterative solutions is, generally speaking, either they will converge to the correct answer, or they will converge to an incorrect answer, or diverge. So you're not gonna wind up in a solution where you just keep iterating forever and you're not going to get an answer out. You're going to get some sort of an answer out. The only thing you have to ask is whether the answer that you get out is the correct structure or not. And there are issues related to that, which we won't really talk about today. Now, one of Joachim Frank's postdocs for a few years was Marin van Heel. And Marin van Heel had some disagreements with Joachim about the best way of approaching 3D reconstructions, and developed this alternative software package called Imagic. And it was written later, but it was first published at about the same time SPIDER was first published. And it used a somewhat different strategy. So it used a strategy where, again, you have to start with an initial model and you start with particles. And again, you make projections of the initial model. But in this situation, what you do is, instead of instead of using the projections to determine the orientations of the particles, all you're going to do is use the projections to determine the best 2D orientation to put the particles in a self-consistent way. So the idea is if you have a particle in some 3D orientation, this is going to help you determine the correct sort of a self-consistent 2D orientation for each type of particle. Then you run principal component analysis on the set of aligned 2D particles and use that to classify the particles and produce a set of class averages. And the idea is that these class averages would then represent different particle orientations. So different 3D orientations of the particle, not different 2D orientations of the particle. And then you could determine mathematically the relative orientations of all of these 2D class averages using a technique known as common lines, which relies on the fact that when you do your Fourier reconstruction here, any two projections intersect along a plane. So the plane where the two projections intersect is called a common line. So if you have a set of 3 slices, let me see if I can go back. Right, so if you have a set of 3 slices, then you'll have a set of 3 common lines. And by determining where the 3 common lines are in all 3 images, you can unambiguously determine the relative orientations of all the particles. And then you can do a 3D reconstruction and you can get around bias problems which might exist with the spider approach. And once you've got a new 3D reconstruction, then you make a new set of projections and you improve your 2D alignments, and then you just repeat this process over and over again. Anyway, so that was an alternative strategy. When we introduced Eman, we did something sort of in between. So we used the projections again, but rather than just determining the orientation of the particles, we classify the particles based on the projections. So we're not doing PCA to classify the particles. We're classifying the particles based on their orientations compared to the projections, and then making class averages. And then this was sort of the unique process here, which was Eman was doing an iterative self-alignment of all the particles within each class to more rapidly converge to the right answer. So what does that mean? So we wind up with class averages again. We do a 3D reconstruction because we know the orientations here. We're not using common lines. Make a new set of projections. We iterate this process. The big difference between this procedure and the spider procedure was that because of the iterative class averaging that we're doing over here, the overall process would only need to be iterated 4 or 5 times typically to converge to the final answer. Whereas if you use the spider approach, it would typically take 30 or 40 iterations to get to the correct answer. So we could basically use this class averaging step as a way of kind of shortcutting and converging to the correct answer more quickly and with less ambiguity. Would get rid of some model bias. Phew. Okay, now we're on to Relion. Now Relion does something kind of similar. It uses a 3D reference and makes a bunch of projections. But now, instead of determining the orientation of each particle, you look at each particle and compare each particle to each projection and determine the probability that the particle is in a particular orientation. So instead of saying, oh, the particle is in this orientation, it looks the most like this particle, you say, well, it looks a lot like this particle, but it also looks somewhat like the particle that's rotated a little bit, and also somewhat like this particle, and also somewhat like this particle. So rather than putting the particle in a single orientation, you put the particle into multiple orientations based on the probability that it's in that orientation. And again, this is a process, it's called maximum likelihood, which has the tendency to converge in fewer overall iterations. The downside is that computing all of these probabilities is extremely computationally expensive. And in the first few years, people weren't really big on using Relion because it was so computationally intensive and required these gigantic clusters to do anything profitable with them, and it was using massive computer resources. Then they came out with a GPU, a graphics card accelerated version of Relion, and that made a big difference. So now people buy these big workstations that have 4 GPUs in them, and then put 2 or 3 of those together, and then they can run their Relion jobs in reasonable amounts of time. There are a number of questions about what Relion is doing, whether it's actually maximum likelihood or not, but regardless of the mathematical arguments, it produces very nice structures. That's, that this has become sort of the standard in the field now, doing these maximum likelihood reconstructions along with CryoSpark, which does the same, doesn't do maximum likelihood. It uses stochastic gradient descent, but runs very quickly and is very automated. Okay, yeah, anyway, there are many more single particle analysis software packages out there, dozens, which just don't have as high usage levels if you go through the database. Really now sort of Reliant and CryoSpark are kind of the two for single particle analysis that people have sort of narrowed down to. That doesn't mean that that's the only way of getting the right answer. These are old slides, but this was an example based on that structure I showed you before, that first paper from Reliant, showing that if you do the same refinement in Eman and Reliant, you get basically the same answer out, and that when Eman does it, it uses a lot fewer computational resources to achieve the same thing. But anyway, and one other example, which was the TRPV1 ion channel. So again, this was the same data reconstructed in both packages, and they both achieve basically the same resolution, and the structures are both quite nice and agree with each other. So, all right. So what can you do with EMAN2? Even if you don't want to run single particle refinements in EMAN2, it's a very nice package for doing sort of generic image processing, file conversion, filtering, masking, all sorts of stuff like that. So it's a nice toolkit. If you know a little Python, you can do even more with it, since it has a nice integration with Python and some integration with Jupyter Labs. We've got some online sessions already on YouTube, which talks about that. And we've been meeting every week to talk about sort of the Python aspect of things. But there's also plenty of command line tools for doing that sort of thing. We can do the whole pipeline of single particle analysis. That's a tutorial you're going to go through in the next week. We have this tilt series alignment and tomogram reconstruction pipeline, which used to be something that people would do in IMOD. In Eman, this is basically fully automated. You take the tilt series, you put it in the software, and it'll give you a reconstruction. There are one or two parameters that you can tweak in certain situations, but for the most part, you can really just sort of follow through this pipeline very, very quickly and get very nice reconstructions, which are easily as good as what you get out of IMOD. We have a deep learning based tool for tomogram annotation and segmentation. We're continuing to develop those tools. That's part of Land's thesis now, actually, is developing some improved tools for doing this. We've got subtomogram averaging pipeline with per particle per tilt methods, which allow you to achieve high resolution. This is very much the same sorts of methods which are being used in other packages as well, which do high resolution subtomogram averaging. So what Reliant does is now in this Reliant 4 release or whatever is pretty much the same sort of per particle per tilt thing. And EM Clarity, which is also available, does very similar sort of process. Sorry about the dog. We just had someone knock at the door. 2D variability analysis. This is something we've had at Eman for a long time. You can make these nice little sort of motion movies showing how particles vary. A population of particles varies in 2D. You can look at dynamics and flexibility and that sort of thing from a 2D perspective. There is also a 3D variability analysis, which is what we're going to be talking about in the third week, or the third, well, sort of, I guess the fourth session is when we'd be trying to talk about that. Then, yeah, I mentioned this already, the Jupyter Python NumPy integration for other stuff. All right, EMAN2 has a complete graphical workflow, handles all the steps of single particle refinement. It includes a project system which keeps track of your data and records all of the tasks that you do when you're going through your reconstruction. So when you go to publish, you can trace back the exact steps that you went through when you did your when you went through your reconstructions. It uses Qt and OpenGL for all of its 2D and 3D displays. Has I/O support for basically all documented cryo-EM file formats, so as a tool for file conversion and stuff like that. It's good. Bunch of image processing algorithms. All right, we'll move on from this. So overall architecture of EMAN2, it's built on top of a C++ core. Then the C is wrapped into Python. We also make fairly extensive use of NumPy nowadays. This wasn't true for a long time, but a lot of the newer stuff uses NumPy and TensorFlow for doing some of the analysis. So we do have a bit of GPU acceleration in a lot of the TensorFlow related code for sort of deep learning sorts of processing. Then we have command line programs. All the command line programs are written in Python. So if you know a little Python, you don't have to know C++ to read the programs and understand what's going on. So you've got the command line programs, which do a sort of individual tasks. Then there are the high level command line programs, which do things like do a 3D refinement or something like that. So these would be things like, convert files from one format to another, or classify a bunch of particles or something like that. The high level programs would be things like do a full 3D refinement. And then finally, we have the GUI, which is the project manager interface, which basically allows you to reasonably run these other high level programs without having to type things in at the command line. So we'll give you sort of an option based interface. And that's it. All of the programs in EMAN2 start with E2, followed by the name, what the program does, and end in .py. Any program in EMAN2 you can call with --help, and it should give you a list of all the options and usually a little summary of what the program does and how. It uses sort of standard Unix command line conventions, which is the name of the program. If you see things in greater than, less than signs, these are required command line parameters. Then it'll take options in the form of either -- option equals value, or -- option. If it doesn't take a value, then there's just no value. And sometimes there are single letter, which are only preceded by a single letter variants of the two dash, the full word options. So sometimes there'll be a shortcut version of this, which would happen with a single letter. Also, in the case where there's an option and a value, you can replace the equal sign with a space, and that also works. There's also another program called e2help.py, which will give you help on various things that are available inside the system. It'll tell you about all the image processing operations that are available. It'll tell you what the good box sizes are to use. So if you just run e2help, it'll give you a list of categories that you can use. There are a bunch of modular classes available in EMAN2, which consist of image processing algorithms of different sorts. So these are sort of the different categories. I'm not going to go into depth in that stuff today. Here's a list of the main file formats that Eman supports. There's a wiki page which has a more exhaustive list of everything. There are a few things excluded from this list, including some of the newer formats which are supported. They're just not in this list, like the EER files that come out of the new Falcon 4 cameras and stuff like that. Those are supported. Okay. Yeah, this is just a summary of sort of recent changes. I'm just going to skip over that for today. So let's talk a little bit about the contrast transfer function, because these are concepts that you'll need to understand for going through the tutorial. Again, to really understand this deeply, you're going to have to know at least a little bit of something about Fourier transforms. But I think you at least get some gist of the idea, even if you don't really understand Fourier transforms very well. So there are two terms that you'll run into in cryo-EM. There's the CTF, the contrast transfer function, and the MTF, the modulation transfer function. The CTF is basically our mathematical understanding of the physics of the imaging process in the microscope. The MTF includes things like motion of the specimen on the stage, if the stage is vibrating a little or something like that, any issues caused by the detector, problems with the lenses in the microscope, that sort of thing. So these are sort of microscope specific things, and these are sort of the fundamental theory of how the physics of the imaging process works inside the microscope. And this is basically to say that when you get this projection image, so when you have your specimen in the microscope and you look, you're summing through the projection, summing through the specimen to get a projection image, what you get, pardon me, what you get out is not the perfect projection of the image. What you get out is the projection of the image modified by the contrast transfer function and the modulation transfer function. So here's a typical cryo-EM image. This is a very old series of slides, but it's still valid. So basically what we're going to do is we're going to take this the region inside this green box here, and we're going to compute the Fourier transform of that region. And if we look at it, we see this. So you see this pattern of circular rings. Okay, so this is the Fourier transform, also known as the power spectrum in this case, of the of that whole image. Now, if we take this power spectrum and we compute rotationally average it and compute a one-dimensional curve, since you can see it's basically circular, then we see something like this. So we see this pattern of sort of almost sinusoidal-looking oscillations in our data. Now, another strategy we can use to make this look a little bit nicer is instead of doing one giant box across the whole image, we can go in and we can box out smaller regions across the image, and we can individually compute the power spectra of these, and then we can sum them together. And what that does is it gives us a fewer data points, but it smooths out the curve a little bit. It makes the curve look a little bit nicer and smoother. So we go ahead and do that process. Now let's take a look at this curve and try to understand what it is we're seeing. Now, we can draw a line sort of connecting all of these zeros of the sinusoidal oscillations here. And we can subtract that off. And now we can just look at the sinusoidally oscillating part of the curve. Now, if we compute the theoretical contrast transfer function of the microscope and plot that, we'll see that it matches, the periodicity of the oscillations matches very nicely. So this is the theoretical CTF in blue. But the amplitudes are a bit off. There's a bit of a difference there. So what is it that's going on here? So what we get in the image on the microscope is a combination of three factors. Okay, so the measured signal is sort of just our final result. That M stands for measured signal, and that consists of the noise. The noise is basically the background in the image. Everything underneath here is noise. And then it consists of the structure factor. The structure factor is the specimen itself, right? So whatever the sample is, that is the structure factor. And that's why in the previous curve, we didn't see perfect agreement between the theoretical CTF and what we were seeing in the image. Periodicity was the same, but the amplitudes weren't the same, because what we're seeing is the structure factor multiplied by the CTF. What I was plotting in blue was just the CTF. We were omitting the actual specimen itself. Now, once we've split the data up this way, we can compute an additional derived value, which is known as the spectral signal to noise ratio. SNR, you'll see the term SNR a lot in image processing papers and stuff, signal to noise ratio. This is a spectral signal to noise ratio, which means that we're looking at the signal to noise ratio at each resolution in Fourier space. So basically what we're going to do to compute that is we know that this stuff is noise and this stuff above the curve is signal. So we basically take the stuff above the curve divided by the stuff below the curve. And that's the signal to noise ratio. And that's a useful construct we can use later on. All right, so now what if we want to do CTF correction? So we'll take a look at this now in a little bit more depth. So again, we have our measured curve, we have our structure factor, and we have the CTF, that's C. And in this case, I've broken out the CTF into two pieces. There's the CTF part, and then there's the envelope function part. The envelope function basically includes the MTF, the modulation transfer function. That stuff's basically absorbed into this envelope function. The CTF is the sort of the pure theoretical part of this. And then of course we have our additive noise again. This is the functional form for the contrast transfer function part. Don't worry, I'm not getting into the math in any great detail, but you can see that it's a sinusoidal oscillation. It's just that the thing that it's taking the sign of is this rather complicated expression S is basically x-axis in Fourier space. It's the spatial frequency, and you can see that it's a sine, but it's a sine of something to the second and fourth power here. So the spacing of the peaks in Fourier space isn't uniform. And then this term here, the sine versus the cosine term, this Q corresponds to the amplitude contrast in the imaging process. I'm not going to go through this in any more detail. This is just a very quick introduction. Sorry. So when we work out, oh, sorry, I missed a slide. Yeah, there we go. So when you work out the best way of doing this correction, basically what we're going to do is we're going to say we have a whole bunch of particles. Each particle is going to have a different contrast transfer function because the focus of the microscope is going to be a little different for each image, and there may be some other imaging parameters that vary a little bit. So what we'd like to do when we average the particles together, either in 2D or in 3D, is we'd like to figure out the optimal way of weighting the average to get the best possible result out. Okay, so in this case, m sub I is the I corresponds to the index of an individual particle. An individual particle in the same orientation, because we're going to average things together. So we have n particles all already aligned in the same orientation that we're averaging together either in 2D or 3D. And then we're going to multiply that by some weight in Fourier space to produce a nice weighted average. And this weight is going to also be a function of spatial frequency of spatial frequency, meaning we're doing the averaging in Fourier space, not in real space, and we may be weighting the different images differently. All right, what do I mean by that? I'll show you some pictures in just a second. Anyway, the solution to that problem, to this problem, is that the correct weighting to do in this averaging process looks like this. There are three parts to it. There's a weight based on the signal-to-noise ratio. There's a CTF correction part, and then there's a Wiener filter part. The signal-to-noise ratio weight handles the fact that if you have one image which has no information at a particular point and another image which has a lot of information, well, then you want to use a lot of information and you want to throw away the no information, right? So you want to weight the images based on how much relative information they have. If they both have the same amount of information at a given point, then you want to weight them equally. But if one has more, then it should be weighted higher. The CTF correction is basically just taking that oscillatory curve we had and dividing by it to make it flat again. Now, obviously, you divide by 0, you get infinity. So there's some problems when you get close to the 0 points in that sinusoidal oscillation. But we take care of that based on the signal-to-noise ratio weight. So at the point where this becomes infinity, when you do the CTF correction, the signal-to-noise ratio weight goes to 0 because there's no information content there. And then the last term is the Wiener filter, and the Wiener filter is designed to damp noise down in an optimal way. Okay. Now, it's okay if you didn't understand all that in great depth. At least you will have heard it once, and when you read through the tutorial, you'll have at least one notch better understanding of what it's talking about in this case. So let's look at this visually. So back to this curve that I showed you before. So we have our theoretical CTF in blue here, and we've got our real CTF in black here. And you can see, again, it goes to 0 at a variety of places. So if we tried to do a reconstruction and all we had was information from this one defocus on the microscope, we would have problems because we wouldn't have any information at these points at all. So what you do when you collect single particle data is you collect data at multiple defocuses. Okay, so this is now showing you, this is CTF amplitude, this was intensity, so that it's a little bit smoother down here. But anyway, this you can see these are the 0 points of the CTF. So as you adjust the defocus on the microscope, it shifts the location of the zeros. So if you collect images at several different defocuses and then average them together with a weighted average, you can then you at any given point in Fourier space, you have some information. So now if we take all of these curves and we add them together, you can see it's not perfectly smooth, right? So if we just did the phase flipping, if we took all the places where these CTF curves were negative here, and made them all positive. That's known as the phase flipping part of the correction. And then we just average all the data together. We'll wind up filtering our data with this kind of rough looking curve. The more different defocuses we have, the smoother this is going to get, but it's still not perfect. So we still want to do the correction by the 1 over the CTF term to sort of bring that back up. Now, this is what you would get if you just did a straight average of all of the phase flip data in a single particle reconstruction. If we include the signal to noise ratio weighting term, that gets us a little bit of an advantage. So we would get something like the blue curve. So we get a little bit more signal out by doing the signal to noise ratio weighting, but it's actually a fairly minor kind of improvement. When we throw in the Wiener filter and the CTF correction, then that takes the curve back up to sort of the 1 where it should be correctly. And then it's only at high resolution where we just don't have much information at all, where the signal begins to sort of damp off. And you can see these little glitches here. These little glitches are because we didn't sample enough different defoci on the microscope to really sort of smooth things out. Okay, so that was the little talk. I just want to spend a couple minutes now looking at some real data, and then I'll take some questions. And I realize we may run over an hour just a little bit, but that's it's fine from my perspective. Feel free to leave whenever you need to. So what I have here is a real data set that was collected on the glaciers. This was collected back before we'd corrected a couple of detector images, and there were some issues with some of the movie alignment and stuff like this. So the images that we're going to be seeing here are more like images that we would have collected on film 15 or 20 years ago, rather than what you'd see now on a modern detector with movie mode correction and stuff like that. But still, it's the sort of thing that you might still see, and we can look at some of the features of some of these images. So we're going to run E2 eval image with the image parameters for our data, and I think, yeah. So these are just MRC images that were collected directly from the microscope. So we can call this E2 eval image with a large set of micrograph files, and it will open several windows on the screen. Let me just get them arranged so we can actually see them. Whoop. Oh, okay. I'm using a smaller screen size than I typically use when I'm working, just so it records nicely for uploading later. All right, so we can see all the different windows that we've got here now. Here, this is the list of all of the micrographs that we have in this data set. We have the various contrast transfer function parameters over here. And there's a variety of different analyses that we can do. We're just sort of seeing the default mode right now. In the default mode, it's basically going through each image, and each of these green squares, it's boxing out each of those squares. It's computing a power spectrum for the square. It averages together all the power spectra, and then this is the power spectrum of the average over here in the left window. And then this up here is the rotationally averaged power spectrum. Now you can see it's very strong close to the origin because of ice gradients and stuff like that. So I'm going to zoom in on this a little bit. And now we can see the contrast transfer oscillations here. So what we're looking at here is the background subtracted curve. If we want, we can look at the, we can look at the raw curve. So here, the blue line, this top blue line, is the raw power spectrum of down here, rotationally averaged. Then the black line is what it decided was the background. So that this basically sort of fitting through the zeros. So it subtracted this blue curve from that black curve to produce the black curve that we're seeing down here. So let me go ahead and turn that off, and we'll go back. at this again. Oh, let me see if it goes away. I'll turn it off this way. Let me zoom back in. All right. Now, taking a look at this image, you can say it looks kind of ugly. There's a bunch of stuff in here which doesn't look like, those are particles floating around in the ice. This is actually IP3 receptor data. So Arena's lab should be very familiar with this. This was test data that we collected as part of the CPRIT grant in our joint cores. So these are individual particles floating around. This is some sort of ice contamination floating around in here. So let's take a look at another image and let's find one which visibly looks a little bit better. So this one visibly looks a little bit better. There's still some thick contamination here. There's some blobs of contaminating ice on the surface here. The particle distribution looks a little bit nicer. We can see up here, this power spectrum looks okay. All right, now let's look at the power spectrum of this compared to the power spectrum of this. Okay, or this. That's actually probably a good one to start with. Actually, let me scroll through here and I'll find one that was particularly demonstrative of certain things. There's particles in that one. Let's look at there being more bad particles in here. Oh, okay. Here's a really good one. This is an example of a particularly bad image in one particular respect. So if you look at this image here, you may be able to sort of faintly see it looks kind of streaked in this direction. Okay, this is an example of an image where the specimen was moving a lot in the microscope. And in this case, it was moving so much that even with movie mode correction, it just can't get it fully corrected. So in the real space image, you see this sort of drift in this direction. And in Fourier space, what that winds up looking like is an asymmetric power spectrum. You just see the central maximum of the CTF here just looks like a one directional thing. If we look at a good image, you'll see that it's got a nice, it looks round. None of these images are actually really good. You can see they all have a little bit of fall off in one direction compared to another direction. You can see it falls off a little bit more in this direction than it falls off in this direction, but this is not too bad, right? This is pretty decent still. Whereas that other image we were looking at here is quite bad. So this is an example of an image that has strong drift. Now, this image, with this ice contamination that we see sort of hovering around the surface, this ring that you see out here is the ice ring. You may see crystalline ice out there, or you may see other types of ice contamination out there. If you see a sort of a strong, smooth ring out there, and we'll probably see that if we look through enough examples here, that is indication that the ice is just too thick on the particle. And if you see that, I'm just going to scroll through a bunch of these until I find one which seems to have a strong, sorry, we had good thin ice at the beginning here. Maybe I'll scroll down later and see if maybe the later images are worse in that respect. You can see a lot of these images are showing a lot of drift. Boy, I'm just not seeing a lot of those, a lot of smooth rings. Huh. I was expecting this to be easier to find bad examples of. All right, well, let's go back to the one we know was bad. So if you see a sort of a spotty pattern out here, that's usually demonstrative of crystalline ice, which is absorbed on the specimen in chunks. Sometimes it may be spread out across the image. Like this image is an image that I wouldn't use. Not only does it have drift in this direction, but it has these big chunks of sort of crystalline ice floating around the image. So it's one that I would just discard completely. Again, this image has very strong crystalline ice, but in this case, it may be more localized. So you might actually still be able to use some of these particles in between the ice if you really want to. Although again, if I see really strong spots out here, I might tend to get rid of the image. Now, if I found an example of a smooth ring, well, we're just going to have to pretend. So if instead of seeing these sort of spotty ring, you see a strong smooth ring out at about the same radius, then that's just an indication that the vitreous ice, the good ice in your specimen, is just way too thick. You may still see a reasonable contrast transfer function in your specimen. We don't in this particular case, but you may still see a reasonably strong contrast transfer function in your specimen, even when you see that ring, but you'd still probably want to discard the data because it means that the signal to noise ratio in your specimen is not going to be good. Now, I'm going through this so fast, it's not actually having time to fit. You'll notice if I adjust the defocus here, I can and hit refit, for example. Normally, when you pull up the curve, pull up the image, it will fit it the first time. But if you go over it really, really fast, it may skip the fitting process. And then if you go back to that image, it'll say, oh, I already looked at that image, and it won't refit it automatically for you anymore. Anyway, this is a tool designed for interactive looking through your data. You don't have to use this tool as part of the tutorial. This is one that has sort of a layer of crystalline ice over the top. Anyway, you don't have to use this tool on any of the data for the tutorial because the tutorial data is all pretty good. I think I left one bad micrograph in there in case people want to sort of look through it and kind of practice. But generally speaking, all the data in the tutorial data sets is good, and you don't have to go through and learn this process. But this, if you're looking at your own data, this is actually a good thing to do. I'm not saying if you collect 10,000 micrographs, you necessarily need to go through all of the 10,000 by hand, but you might want to look through a few dozen of them just to make sure there don't seem to be a lot of really bad images in there. If you go through, say, the traditional Reliant processing, run your frame alignment, then GCTF and run Reliant or something like that, it's not always going to do a good job of catching some of these images to get rid of them. If they have a strong CTF, it may include them in your data, and it may actually hurt your reconstruction rather than helping it. If there's only a few, it's not going to be a big deal. But if half of your data set, and it does happen from time to time, if half of your data set is weak data, then it may impact your reconstructions. Okay, I think that's all I wanted to talk about today for this sort of introduction. Are there any questions about any of this stuff that I've gone over already? Again, you'll go through the tutorial over the next week. So please come to the next meeting having tried the tutorial yourself at least once. You don't have to raise your hand, just unmute yourself and talk. It's okay.
Yeah, I had a question. So besides sampling at different defocus points, why does noise increase with increasing spatial resolution or spatial frequencies rather?
Why does the noise increase? You mean
Yes.
what? Well, so it's not so much the noise is increasing, it's the signal is decreasing. So the signal to noise ratio decreases with spatial frequency, but it's not because there's more noise, it's because there's less signal. And that's basically optics. You get when you image with a lens, the higher the resolution you get to, the finer the details you look at, the less signal you get out of the lens. There are several factors that go into that in an electron microscope. That's what those MTF terms that we were talking about. We're trying to look at near atomic resolution here. So one of the big factors on most microscopes is beam vibrations. Stage vibrations. So even if you try to keep the stage perfectly still, if it moves at the level of an atom or two, if it moves just a few angstroms, that's going to come through in the imaging. And if it's moving too fast fast enough that there's blurring within a 15th of a second or a 30th of a second, then even if you do motion correction, you're not going to be able to correct for that. That's one factor. The optics of the microscope, there is a damping factor for the optics of the microscope, although that's pretty good now. You can still get information out past 1 angstrom resolution, even with the damping of the microscope. The detector is another factor. So the physics of how the electrons interact with the detector means that you don't get perfect localization on the surface of the detector. So the size of the pixel in the detector is somewhere around 7 microns. And when an electron at 300 keV or 200 keV impacts the surface of the detector, it doesn't just stop. It actually interacts, and then it interacts again and interacts again. It basically scatters its way through the detector, and it doesn't just produce one flash of light. Typically, it'll produce a bunch of flashes of light over a region on the detector. So every flash isn't just in the middle of one pixel. It actually spreads a little bit to neighboring pixels, and that smears things out. And detectors try and correct for that somewhat, but you can't correct for it perfectly. So that causes another resolution limiting factor. All of these different factors basically come through as degradation of the signal at higher resolutions. And the noise actually decays at higher resolution, just doesn't decay as fast as the signal does, because some of the noise sources are not dependent on that. Is that enough?
Thank you. Yes, thank you.
Okay.
Thanks.
All right. Any other questions? Okay. So everyone who's going to participate again next week, try and go through the tutorial yourself once. If you went through the single particle tutorial once a long time ago and you're happy and you want to just use your own results for purpose of the discussion, that's fine too. It's not like I'm going to demand that everyone show their results up on the screen. But if I show my results and you see your results weren't as good as my results, then I'd like to actually sit down and go through some of those results and try and figure out why didn't your result come out as nice as someone else's result, and that sort of thing. That's where I think a lot of the learning experience will come from. So if no one does the tutorial, then obviously we won't have much to talk about.